All right. It sounded like everybody in breakout rooms got the right answer, which is good. Is this making sense? It's a ton of stuff to keep track of. I fully acknowledge this is a ton of stuff to keep track of, but you got the right answers in breakout rooms. You're good. This is making sense. That question.
So when do we use the unit step function? When
there is an e to the as out in front. So that's when that unit step function gets used. So remember what we talked about at the beginning of class yesterday and today. The inverse Laplace transform of e to the negative as times capital F of s is this unit step function. I'll write it as use of a of t, or remember you can do u of t minus a either way. F of t minus a. So this e to the negative as out in front, that is what indicates to you that you need to use the unit step function. That's what you're looking for. All right. Other questions? I can't see you, so you need a virtual hand raise now. Other questions? Other ones?
Yes.
Daniel,
Wait,
yep.
You can hear me, sorry. So could you just like say the answer again one more time? So
yes.
or the second part, yeah.
Yeah, so it's gonna be, let's see if I can write it from memory. 1/8 sine of t minus 1/24 sine of 3t minus u of t minus 2 pi times the quantity 1/8 sine of t minus 2 pi minus 1/24 sine of 3 times t minus 2 pi.
That's okay.
Yeah. And one of the breakout rooms said, we have t minus 2 pi. Can we make those into just t's because we have a sign out in front? Yes, for the part inside the parentheses we can. So this could be just a sine of t, and this could be just a sine of 3t. The u out in front, though, is not a periodic function, so that has to stay. You can't get rid of the minus 2 pi there. That part has to stay.
Okay.
Okay. Anybody else? Other questions on these? Other ones? Other questions on these? Bethany, yes.
Oh, I'm still unmuted. Okay.
You're good.
No, on the sine of 3 times t minus 2 pi, is that fully periodic like that?
Yes, you would have to split it out a little bit. So what you'd have to think about is the fact that this is sine of 3t minus 6 pi, right? If you distribute through. And because you have a shift of 6 pi, that is also periodic. So a shift of 2 pi, of 4 pi, of 6 pi, all of those are going to work and you can shift it there. So that one is periodic as well, yes. Any other questions on this example? Otherwise, we got one more topic to talk about today. Anything else? Okay. One more then. Transforms of periodic functions. Transforms of periodic functions. Transforms of periodic functions. Okay, we're going to put down a theorem and then I will demonstrate how this works. So my hypothesis is that little f of t is periodic with period little p. So remember what that means. If f of t is periodic with period p, that means if you shift f of t p units either to the left or to the right and overlay your graph, it looks exactly the same. That's what periodic with period p means. Here's my conclusion. The Laplace transform of little f of t is 1 over 1 minus e to the negative p times s integral from 0 to p e to the negative s times t f of t dt. That's a disaster and you're thinking, why are we doing this? 1 over 1 minus e to the negative p times s, integral from 0 to p, e to the negative st, f of t dt. That looks terrible, yes? Yes, you're allowed to say that looks terrible. Here's the thing. The alternative is doing this by the definition of Laplace transforms if we have weird periodic functions. And the definition of Laplace transforms has an improper integral. You would have to do a limit as b goes to infinity. That's even worse. So this is not an improper integral, and that's why this one is better. It's a little messier, but it works much better because there's no improper integral and no limits that you have to deal with. That's why this is an improvement. Really, I promise it's an improvement. Let me show you an example, and then I think there's also one on your homework. So for example, here's my function. We'll draw it for you. It looks like this. It is going to be a height of 1, and then we are working on increments of a's. So a, 2a, 3a, 4a, etc. It bounces back and forth between 1 and 0. So bounces back and forth between 1 and 0. And I'm not super concerned about where the endpoints are. They can either be at 1 or at 0. It's not a huge big deal. So bounces back and forth between 1 and 0. Okay. This has a name. It's called the square wave function. Square wave function. It's kind of like a sine or a cosine curve, except it's flat. So it goes up and down. That's why it's called the square wave function, because it's nice and flat. So we want to find the Laplace transform. All right, this thing is periodic. Yes, this thing is periodic. And my period is equal to 2a. Not a, but 2a, because if I shift this 2a, then I'm going to get exactly back what I started with. Periodic with period of 2a. And my function then looks like little f of t is 1 if t is less than a, and 0 if t is bigger than or equal to a. And this is for t between 0 and 2a. So I only have to define my function on one little piece, and then I've got the periodic part that tells me exactly how it behaves for the rest. So we've got 1 if t is less than a, and 0 if t is bigger than or equal to a. Just on this first chunk right here, this first period. That's not the function in general, but that's the function in one period, and that's all I really need. So using my definition of my Laplace transform, I am going to have, and this isn't going to be so bad, I promise, I am going to have the Laplace transform of little f of t, 1 over 1 minus e to the negative negative a times s. My period is a in this case. So e to the negative a times s. And then I've got to do an integral. That's not right. Let's try 2a, sorry. E to the negative 2a times s. My period is 2a. E to the negative 2a times s. Integral from 0 to 2a. E to the negative s times t, little f of t dt. That's my definition. That's my definition. That's what I'm looking at. So I got to split this integral into two parts because my function is defined differently. So 1 over 1 minus e to the negative 2a, I set in front, and then we're going to have two integrals. Integral from 0 to a, e to the negative st times 1 dt. That's the first definition of my function if I'm between 0 and a. So integral from 0 to a of e to the negative st times 1 dt plus the integral from a to 2a e to the negative st times 0 dt. That's the way my function is defined from a to 2a. So we've got two different integrals that we're working with here. The first integral, my function is 1. The second integral of my function is 0. 2 different integrals that I'm working with here. And the second integral is spectacularly cool because there's a 0, so that whole second integral goes to 0. Yay, that's fantastic. The first integral is really, really easy to evaluate too. So I still have 1 over 1 minus e to the negative 2 times a times s. And then we're going to get a negative 1 over s e to the negative st, evaluated from 0 to a. U substitution gives me a negative 1 over s out in front. U substitution gives me a negative 1 over s out in front. So negative 1 over s, e to the negative st, evaluated from 0 to a, plus that extra fraction out in front. And so this gives me 1 over 1 minus e to the negative 2as, negative 1 over s, e to the negative a times s, minus negative 1 over s, e to the 0. I plug in a, plug in 0, and subtract. And you can simplify that if you want to. That second part just goes to 1. So we can do 1 over 1 minus e to the negative 2as, negative 1 over s, e to the negative as, plus 1 over s. So you can simplify it a little bit if you want to by making that e to the 0 just go to 1. Look, no limits, no infinities, no improper integrals, no dealing with this function with infinite period. We just have to do it once on the period, and then we are good to go. So even though this function, this theorem looks horrible, it helps you not have to be able to evaluate improper integrals. That is good. That is why this is beneficial. Do a virtual hand raise with questions on this before I stop sharing my screen with you. Any questions on this example here? I'm seeing no virtual hands raised. The words that I never thought would be a part of my vocabulary and are at this point in time. Okay, so that's today. We've got from yesterday and today, we've got transforms of piecewise functions. That was what we spent most of our time on. And then transforms of periodic functions was the very end of class today. Transforms of piecewise functions and transforms of periodic functions. There is a lot to keep track of, and that is why you can absolutely have a cheat sheet for the next test, totally allowed. It's just keeping track of when do I need a u, when do I need an f of t minus a, when do I need an f of t plus a, all that fun stuff. But we're feeling mostly okay with this? Doing all right? Yes, yes. Yes, okay. The homework for today, I think, is going to have some differential equations on it for you. So it's kind of going to be what we did at the beginning of class. Now that you know how to do the transform of the right-hand side, let's put it into a differential equation and do it that way. So that'll be the homework. Okay, remember please that we do in fact have class on Monday. We do have class on Monday. So remember that. I will try to remember to send you an email this weekend, but we do have class on Monday. And that's on your schedule. And then next test on chapter 4, a week from Friday, April 17th. Last call. Anything else for questions? Grant, yes.
No class Friday, correct?
No class Friday. Correct. So no class Friday, but class on Monday. Anything else? Other questions? Anybody, anything? All right then, if you have some time and you are inclined, fill out the survey, fill out that Google form to tell me how things are going if you haven't already. Otherwise, have a lovely Easter and I will see you guys on Monday. Thanks guys.